a set and an element, and also we discuss the diameter of a set. So the most important thing is that you can see that we have defined the concept of a metric by using the fundamental properties of the Euclidean metric. In that way, you can see that how we can define, how we can measure the distance between any 2 points in an arbitrary set, not necessarily in the Euclidean space. So this we have seen, and we have also given several examples even in infinite dimensional spaces, namely in the LP spaces, C0 spaces, C01 spaces, set of all continuous functions, real valued continuous functions defined on the closed interval AB, and so on and so forth. And then we defined the bounded and unbounded metric spaces, and also the distance between two elements, and the distance between a point and a set, and between the two sets. And then we, of course, we have given a plenty of examples related to all these definitions and results. In the first week, we have all covered all these things. And then in the second week, we have extended the idea of the open set, closed set in the real line, which you have studied in the course of reanalysis. So how we can do it, as you have seen that when we consider the open ball or closed ball in the real line, then we always use the idea of the distance. So same idea of the distance, now we have borrowed to the arbitrary set. Okay, and where we have already defined a metric. Okay, that is nothing but it is the that is nothing but it is the it defines the metric. It defines the distance between any 2 points in an arbitrary set. So by using a metric, we have defined the closed sets, and we have defined the closed sets and closed sets. Not only this, before that we defined the closed and open balls, or you can say that closed and open spheres. And we defined the interior point and the interior of a set. And you have seen it is almost similar to the one which you have studied in the course of reanalysis. But the only difference is that there you use the Euclidean distance, here we use the metric. And we defined the neighborhood of a point, limit point of a set, closure of a set, and closed sets. So this we covered in the second week of this course. In the third week of this course, we have defined the boundary of a set, okay, or you can say that the first boundary of a point. Okay, then we defined the exterior points and the set of all exterior points. And of course, as you have seen in all the courses, you should have the concept of subspaces. So same as here, we have defined the subspace of a metric space, which is nothing but a subset of a metric space is a subspace of the metric space, provided that the restriction of the metric on the subset is also a metric. So this way we have defined the subspace of a metric space, and we have seen that how a ball or how a closed set or a open set in a subspace. For example, if you consider the closed interval 0, open interval 1, then as a whole space, this set is closed as well as open. because we have mentioned that all the whole spaces are closed and open. So this set is closed and open. But if you will consider this set as a if you will consider this as a subset of R with the Euclidean metric, then it is neither open nor closed. And in the other way, if you consider, for example, set of all non-negative real numbers, okay, and this as a subset of the non-negative real numbers. So how we can define an open ball in this subspace and the closed ball in the subspace, which would not be the same as in the whole space. So this we have given all such concepts in the third week, and beside that there are we have seen several results related to the subspaces. For example, if you have an open ball, then in the whole space, then with the help of that open ball, you can define an open ball in the matrix. That is nothing but if you have an open ball in the whole space, take the intersection of that open ball with the subset, and that would be the open ball in the subspace. Okay, so this we have done in the third week, and in the fourth week we have discussed the convergence of the sequence. It is a very important topic, and the convergence of the sequence. As you see that nowadays everybody is talking about the algorithms. Okay, and we say that the algorithm, the sequence generated by the algorithm converges to some point. Okay, so what we will do, we say that the sequence is converging to some point. It means that that point is the solution of the problem. Okay, or we can say that the distance between the number of iterates and the exact solution of the point is less than with some very less quantity. Okay, so that is the basic thing. So we discuss the convergence of the sequence. As you know that in the real line, you have a sequence xn converges to x, provided that for every epsilon positive, there exists a positive integer n, such that the mod of xn minus x is less than epsilon whenever small n is greater than or equal to capital N. That was the definition. So what is the difference here is how we can do it, because in real life the sequence we consider the sequence of real numbers. Now here in the metric space, the space may not be an Euclidean space. It can be any arbitrary space, as we have seen in the first lecture that there are several infinite dimensional spaces. Namely, you have seen that L infinity, LP spaces, C0 spaces, S space, C0 AB spaces, all these are infinite dimensional spaces. Okay, for example, set of all real valued continuous function defined on a closed interval is 0, 1. So the question is, if you have a sequence of functions, okay, then how can you say that it converges to some point? So for that, we have to define the idea of the convergence of a sequence in a metric space. Keep in mind, metric space is a set equipped with a metric. That is to say, by using that metric, so we can find the distance between any 2 points in that set. So we replace the distance, we replace the modulus x mod of xn minus x by which is equal to what? Which is nothing but is the distance between xn and x. So here is we in this week we defined the idea of the sequence. First, then the idea of the subsequence in a metric space, and then we discussed the convergence of such sequences. We have given a penalty of examples of convergent and non-convergent of the sequences. We have also considered the convergence of the sequence in the subspace. And we also gave we have also given the definition of the Cauchy sequence. Keep in mind, in reanalysis, the Cauchy criteria provides the necessary and sufficient condition for the convergence of a sequence. But in general, it is not true in the case of metric spaces. So we just defined the definition, we have given the definition of the Cauchy, of a Cauchy sequence. And then we have discussed under what condition a Cauchy sequence, we have seen that every convergent sequence is Cauchy, but Cauchy sequence need not be convergent. So if in which sets or in which spaces a Cauchy sequence is convergent, it is called complete metric space. That we discussed in week 5. So in week 5, we discuss the complete metric spaces where every Cauchy sequence is convergent. Okay, and then we have given several relations between several examples of complete metric spaces. We have also discussed several examples of non-complete metric spaces. And we have also seen that a space can be complete with respect to one metric, but it cannot be, or it could not be metric with respect to the other metric. So the space is complete depends on the metric. This we have illustrated by giving some examples in week 4. Okay, in week 5, we have also given the relation between the completeness and the closeness, and we defined a very nice theorem that is known as the Cantor intersection theorem. So we have explained the Cantor intersection theorem, and then we have also given the converse, how we can write the converse part of the Cantor intersection theorem. Of course, it is not exactly the same as the converse, but we can say that we have discussed the convergence, we have discussed the converse of Cantor intersection theorem. And at the end, we have seen that because you see that there are many non-complete metric spaces. Of course, there are many complete metric spaces. But the problem is that if you have completeness of a metric spaces, and then you see that question is that if we do not if we do not have a complete metric spaces, can we make it complete or not? Yes, every non-complete metric spaces can be make as a
प्रशांति का नंबर कहाँ होगा?
And that space is called the completion of the metric space, which is non-complete. So we have defined the completion of a metric space, and we have given a very nice result which provides that every non-complete metric space has a completion. That is to say, as a metric space which is complete. And what is the property? Property is only that you take you take a non-complete metric space and take all the limit points of the sequence in this metric spaces. Okay, and that space would be a completion of the non-complete metric space. So this we have given in chapter we have given this in chapter 5. What happened? Okay, then in chapter 6, we discussed the dense sets. We discussed the separable spaces. We discussed the nowhere denses. We discussed the first category results. We discussed the first category, second category theorems. We discussed the very important result which is known as Bayer category theorem. Okay, now the separable metric spaces are very important, and we have given a plenty of examples of separable metric spaces. We have also given the examples of non-separable, and that is to say the metric spaces which are not separable are called non-separable spaces. We define the dense sets. We have given the definition of the dense set. We have given plenty of examples of the dense sets. And then in 7th week, we consider the compactness. How we can define in the real analysis, usually we say that a closed and bounded subset is compact. But this is not true in general metric space. So how we can define the compactness in the general metric space? So for that, what we did, we defined the cover. We define the cover of a set. So by using the open balls, we define the cover of a set, and then with the help of the cover, we define the compactness of a metric space. And we have seen then every metric space is closed and bounded, but every closed and bounded metric space may not be compact. So this we have seen, and we have also given several characterizations of we have given several characterizations of compact metric spaces. Namely, we discussed the several properties and criteria for compact set. And we have given a plenty of examples of compact and non-compact sets in a metric space. Of course, if the whole space is compact as a set, then we say that it is a compact space. So a large number of examples are given. We have already given a large number of examples of compact spaces in the 7th week. In the 8th week, we discussed the finite intersection property. Okay. The second is the relation between the compactness, completeness, closeness, and the finite intersection property. So this we have discussed in chapter in week 8, because there are several examples, and for every result we have provided the examples where the converse is not true, or we have illustrated all the exam results with the help of the examples. Then in the 7th week, in the 9th week, we define the Bolzano-Weierstrass property. We defined the sequentially compactness and totally boundedness. And then we have seen that compactness, Bolzano-Weierstrass property, and sequentially compactness, all these are equivalent to each other. Keep in mind, these results are not true in other spaces. So here is namely, these are not true in topological spaces, but they are true in the metric spaces. So Bolzano-Weierstrass property, and sequentially compactness and compactness all are equivalent. So to prove that a sequentially compact metric is Lebesgue covering lever. And for that, we defined the Lebesgue number. You might be remembering that in chapter, in week 9, we defined the Lebesgue covering lever and Lebesgue number. And then with the help of these, we proved that three concepts, namely compactness, sequentially compactness, and Belzano-Weierstrass property are equivalent to each other. And then in the 10th week, we discuss the continuous functions. As you have seen in the definition of the continuous function, in the reanalysis, the idea of the distance is involved. So same, because in the metric space, we have the idea of the distance, so we can define the continuity of a function defined on a metric space to another metric space, because both the metric spaces, the domain space and the range space, both have metric. So with the help of these matrices, we can define the continuity of a function from a metric space to another metric space. And then we discussed the several characterizations of several characterization for the continuity of a function from a metric space to another metric space. We have given a large number of examples where the function from a metric space X to another metric space Y is continuous. We have also given examples where the metric space, where the function from a metric space X to Y is not continuous. So all type of examples are given. Okay. So then in 11th week, we consider the uniform continuity. So you have seen that in the continuity, okay, continuity means for every epsilon, there exists a positive integer n. For every epsilon, there exists a delta positive, such that the distance between f of xn, the distance between the image of the sequence and f of x is less than epsilon whenever the distance between x and xn and x is less than delta. So here is delta depends on the epsilon. Okay, so and the point x. So if delta works for every x and epsilon, then we say that it is uniformly continuous. So this we have discussed in the 11th week, and we have seen that we have also seen that when a continuous function can be a uniformly continuous, and that is true. That is only happened if the space is compact. So we have seen that we have discussed the continuity on a compact space, and we have also proved that the continuous image of compact set is compact.
Okay? Recording in progress.
And then the uniform continuity, and we have defined the homeomorphism and isomorphism. So, and we have seen several examples. We have seen the relations between the uniform continuity, homeomorphism, isomorphism, continuity, and so on and so forth. At the end of this course, that is to say, in the 12th week, we discuss the equicontinuity. You see that if you have a sequence of functions, so you will have different type of continuity. That is to say, pointwise continuity and uniform continuity. Pointwise continuity means that f of Fnx converges to Fx. So it means that it is depending on a particular point. So if it is true for all x, you have the uniform continuity. So here is the Yuki continuity provides the very nice results about the uniform continuity on a metric space. Then finally, we give a glimpse of fixed point theory. Of course, you can find several books, several courses on fixed point results. But here we have given only glimpse of fixed point theory. And so we defined the fixed point. What do we mean by fixed point of a mapping from a metric space to itself? Okay, the mapping should be the self, not non-self. That is to say, a mapping, say for example, T is the mapping from a metric space X to the same space X. Okay, then we defined the idea of a fixed point. And we have given again several examples of a fixed point. Okay, several examples which has a fixed point, several examples of a metric of a mapping which do not have any fixed point. And we also given a very important result, as you can say that one of the best results in the nonlinear analysis, that is called Banach contraction theorem. So we have proved that every contraction mapping defined on a complete metric space has a unique fixed point. So here is in the Banach contraction theorem, we have the mapping should be contraction. So we defined first we have given the definition of the contraction. We have given the definition of the contractive. We have given the definition of non-expansive map, but we have not discussed non-expansive map, but we have also seen the relation between the contraction, contractive, and non-contractive. And we have given several examples where a contraction map is a contraction map, even contraction map do not have a fixed point. But the Banach contraction theorem says that every contraction map defined on a complete metric space has a fixed points. And we have given the examples of the mappings which is contraction, but the space is not complete. So the mapping does not have a fixed point. We have also given the example of a mapping which is not contraction but defined on a complete metric space, okay, does not have any fixed points. So all these things we have discussed in this course. Now I invite to all of you, if you have any question or any queries related to this course, or you have any doubt in any definition, any result, please you may ask now. Anybody? Munir?
Hello, sir.
Yes. Any question?
Sir, I have one doubt. At that time, I read the book of you, whatever you provide. So there, I see every Cauchy sequence is convergent in metric space. The converse is not true. That means this statement is not true. So, sir, when I see in particular discrete metric space, this result is true. Sir, how I don't understand how this, in particular this metric space, this is true. In discrete metric.
No. Actually, you see here is with respect, of course, again, the important thing is that when we talk a sequence is converging to a point, it means that a sequence is converging with respect to some metric. For
Okay.
example, as we have seen that there are several examples, okay, where we
Okay.
have provided several examples where, for example, C01. Okay,
Okay.
C01 is complete with respect to one metric, but it is not complete with respect to the other metric.
Okay.
So same as the completeness of a metric, the convergence of a metric depends on the metric.
Okay, sir.
Same as
Understand.
the completeness depends on the metric. Okay.
Okay. Sir. Okay, sir.
Any
Thank you.
other question?
No, sir. Thank you.
Sir, I have a question.
Lukman, you can ask some question.
Sir, during-
Sir, as you described that every Cauchy sequence is convergent in a complete metric space. Sir, what is the significance of this Cauchy sequence which is making the space to be complete? Physical significance of the word complete.
Physically, you see that if you have a complete metric space, it means that you can say that if you are having any sequence, okay, which is Cauchy, okay, because you see
Yes,
that
sir.
if you have studied in the course of real analysis, the Cauchy criteria is one of the best criteria to prove that the sequence is convergent. And if you have, for example, nowadays in the computer, you write an algorithm. And in the algorithm, you need to prove that the sequence must converge to a point. Okay, so
Yes, sir.
in the in the Cauchy sequence, you in the convergent of the sequence, you check after a finite number of a term of a sequence, the distance between the terms after a finite number of terms and the limit point is very, very small.
Yes, sir.
Okay, but in the Cauchy sequence, you need to you take any two terms. Okay,
Yes.
after a finite number of terms, and check any two. Take any two and check whether they are very close to each other or not. If they are very close to each other, then it is sufficient to say that the sequence is convergent. So it is
Yes,
good
sir.
to check instead of checking all the points after that has the distance between them with the limit point is very, very small. Just you check any 2 point. So it is a very good thing, sir, to see that with the Cauchy criteria, we can have the convergent of the sequence.
So we can say that in a complete metric space, if the distance between terms of a sequence is decreasing after some finite number, then definitely the sequence is going to be converged.
Decreasing, no, not decreasing. Decreasing doesn't mean, it means that after a certain finite number of terms, okay,
Yes.
the distance between the other terms, okay, is very, very
Yes, sir.
small.
Okay,
It may increase, it may decrease, no problem.
okay, sir. Thank you.
So if there is no question, then we can stop this live interactive session on the. Yes.
Sir, discrete metric makes every set bounded. So, sir, even our universe becomes bounded under discrete metric. So it's very interesting. So, sir, is there any real application of the discrete metric, sir?
We are unable to hear you properly.
Sir, am I audible?
Yes, your voice, yes, you can speak little loudly.
Yes, sir. Hello. Hello, sir. Am I audible?
Yes, we are audible, but your voice is not very clear. So you can speak loudly.
Okay, sir. Sir, actually, a discrete metric makes every set bounded. Even our universe becomes bounded under the discrete metric. So, sir, is there any real life application of the discrete metric where this metric is used in our real life?
Yeah, you see that in the discrete metric, is the only thing is that because discrete metric provides the distance between any 2 points is either 0 or 1.
Yes, sir.
Okay. So
Yes, sir.
it means that we can always define a metric which is called discrete metric on a set. But in general, you see that if you say that the distance between any 2 points is 1, okay,
Yes, sir.
it is not very significant in the general in our real life problem, but definitely it might be useful in some non-trivial examples, namely in some infinite dimensional spaces.
Yes, sir. Thank you, sir.
So yeah.
Okay, sir. Thank you, sir.
So okay, so we close this live interactive session on the course of metric spaces. And thank you very much, everybody, for joining this session. Okay. So thank you very much. Faraz, you can include the first half. You can include the previous talk in this live interactive session. So you can combine
Yes, sir, I
it
will merge the videos.
Hmm?
Yes, sir, I will merge the videos.
Okay. Thank you very much.
Prashanti, should
Okay.
we leave? Should we finish
Yes,
the
yes.
video?
Yes. Prashanti, can we leave the video?
Okay, then let's finish. We'll see later on if she
Okay.
requires
Let us
anything else.
finish. Okay. Thank you very much.
Okay.